All right. Hello, everybody. I'm Jerry Brown, PhD student at Oklahoma State University. I'm going to be bringing some information about 8 different soil moisture sensors that have been in a longstanding sensor test bed there in Oklahoma. So a little bit about soil moisture. I think we've covered the gamut on what we can use soil moisture for here today. Coming last, I think we've kind of covered it. We use it for everything to guide our land and management decisions. So this research here is evaluating the accuracy and the reliability of these soil moisture sensors, basically to inform people, the end users, and make better decisions. So a little bit about this test bed site. It's in Marena, Oklahoma. MOISST, the Marena, Oklahoma Situ Sensor Testbed. 2010, it was started basically a standardized test bed for all these different types of sensors in one site. So there's one location. There's 4 different sites, and I'm sorry if you can't see it really well. Let's see. There's 4 sites: A, B, C, and D. This Mare site, you've heard of the Oklahoma Mesonet. It's been mentioned today. That is the Marena, Oklahoma Mesonet site. The location here, it's about 800 meters by 800 meters, approximately a quarter section. And you can kind of see some of the long-term, it was agricultural land years ago. You can still see some of the terraces left in this satellite picture. It doesn't really show it, but the grade, this all goes downhill, it slopes down. There's probably maybe 20, I think it was less than 10 meters difference in the height, the elevation of all these sites. But there's 4 test bed sites. 2016, there were some additional sensors installed, and earlier this year, we installed some sensors for another project at the same sites. So here's a picture of one of them, of one of the sites. So these sensors were evaluated at 10 and 50 centimeters. At 30 centimeters at one site C, there's a sandy layer down there. We couldn't get, there's not sensors below that. There's a sandstone layer. So that's the only one that's different, but all the rest of them, 10 centimeters and at 50 for the deeper depths. In 2010, you can see the sensors that were installed were the Campbell Scientific 229 and the 616, the Stevens Water Hydroprobe, the Syntec EnviroSmart, and the Delta T Theta. In 2016, the Acclima TDR 315, that Decagon GS1, and that Campbell Scientific 655. All of them, the neutron probe that was mentioned, that's what I use as the standard. And all of those data were collected from April to October of 2020. So a little bit about that hydroprobe, the neutron probe there, basically taking moisture measurements in the subsurface. It has a radioactive source. You lower that down at each depth. There's already a tube in the ground. It's that probe is sitting on a tube. This stand that's set on top of the tube. The tube only sticks up about 5, maybe 10 centimeters above the ground. Normally encapsulated, just a piece of PVC, a cap on it. But you take that off, put this probe on it, and there's a little latch here, and little increments that when you drop the source down at whatever increments you've set that at, so 10, 30, 50, 70 centimeters. But those, once you drop the probe down, sends off neutrons. They're thermalized by the water molecules, the hydrogen, and they're counted by the detector. As the water content goes up, you count more. They're calibrated against the soil sampling to achieve the MAD of less than equal to 0.028. And that was with our soil sampling. So a little bit on here are all of the soil samples from all the sites, all the properties. Really, I want to point out the B and C. You can see the difference in the sand and the clay. Most all of them were pretty consistent, but at site C, you couldn't go down really deep. There's not much clay, and it's a lot of sand. And as you can see at B and in the deeper depths, we're really different here in the amount of clay, amount of sand. But at all of them, at the deeper depths, 50, you can see there's 40%. You can see 57 and 45. It's a lot of clay down on the 50 centimeter samples here. And we've got all the textures out there. So on to the data. I hope everybody can see this. I was kind of gauging the light back there. These are the surface soil measurements at 10 centimeters. On the left side are the sensors that were put in 2010. On the right side, the sensors that were put in 2016. You can see that site A and site AA, it's still the same site. They just, when they added the new sensors, they just labeled it AA, different logger box and everything. So I guess one thing I'll point out first, you can see temporally that they all tracked pretty well on both of them. There's a few of them here that tended to overestimate, and the 229 and the 229, it sort of has a sharp drop off there on the dry down. Like I say, I hope everybody can see that. But for the most part, they track pretty well with the neutron probe measurements. You can see the circles. That's the days that we took the measurements with the neutron probe. Large gaps, like right here, those were issues with like the battery or a solar panel. And that's why there's no data there. So that's the 10 centimeter. So now it gets changes up a little different when we get to the 50 centimeter. Once again, on the left side are the sensors that were installed in 2010, and the right side, the ones in 2016. But you can see the difference. Now we get to the more clay sites. The sensors tended to overestimate the soil moisture a little bit more. The range is from 0 to 0.7 on the y-axis. We still had the same kind of dry down on that 229, although it's a little bit better than it was on the shallower depths, but it still took a while. Temporally, they still tracked really well, and you can just really see the difference here at site C. Kind of once again, where there's not much clay, it tracks really well. But these are, when the clay content went up, at least on the sensors on the left, they tended to overestimate the soil moisture. So this scatter plot here just shows all of the sensors along with the neutron probe measurements plotted on a 1-to-1 line, with the sensor volumetric water content on the y-axis and the neutron probe on the x. Pretty obvious looking at them here. The TDR 315, the GS1, they tracked really well visually. You can see even the others, the 655, the Hydra, they all tracked pretty good. The blue dots represent the 50 centimeter depth and the 30 centimeter depth at site C. And you can just see they still tended to overestimate at the deeper depths. And that's generally due to the clay content. The 229 in the bottom right, it's kind of had almost a rectangular appearance with that. I think that's because of on the wet end and the dry end, it was just sharp. There was no gradual on and off. It was either wet or dry. This one's busy, and I apologize for that, but here's all the statistics. On the NSC, the Nash Sutcliffe and the MAD, we ran on all of them. I just highlighted a couple of the more prominent ones. The average NSC for that TDR 315 from a negative 0.08 to a 0.906. And the same with the MAD from a 0.17 to a 0.53. Those were the best ones. Each column here, that's the sensor, and with its NSC and MAD. The top is the 10 centimeter and the sub is the deeper depth at the 50 centimeter. All the way on the end, that's the site average with the NSC and the MAD. You can see the average for the NSC for a site, what it ranged from was that negative 98 to a 0.589 for that site and depth. So this graph here, we got the MAD on the y-axis versus clay content. This kind of says a lot about what we've seen with all of them. So we thought it would be good to show it with that clay content, and just visually, you can just kind of tell up to around this 25 to 30%. There's not much difference. The MAD stayed pretty consistent with all the sensors. It's when that clay content started going up that we started getting more dispersion. So yeah, when the clay content less than 30%, they're relatively consistent. And you can see that the 616 and that Hydra, they showed a little greater sensitivity with that higher clay content as shown in the graph. So the results, soil texture, overall sensor performance. I think that's been said a lot here today. We've talked about the kind of texture you've got, which kind of sensor you're going to want. That was kind of shown in most all of these pictures. The different dynamics between the sensors. So all of those sensors, there were capacitance, there was transmissional TLO, TDR. So there's different types of sensor technologies here. So, and the last one, that issues with missing data over the time period. Choosing a sensor, that's kind of hard. You can look at all these different sensors, and just like I mentioned, they're different technologies. They're all in the same test bed. But as far as trying to choose one, you just kind of have to look at where you're at, I suppose, and what kind of textures you have and what's your goal, what you plan to do with that data. But issues going forward, there would be a need to kind of maybe install some other different sensors, some newer ones in there, and try to look at some of the missing data, see if we can. I haven't researched that out, why some of the sensors there weren't data there, or there were just pieces of it missing. But some of that could be done kind of in the future. So with that, yeah, I'd like to acknowledge the USDA ARCS for this research and the support we were getting, and Chris Stansberry, the manager at the Oklahoma Research Station, where it was conducted. And with that, I'll field any questions.
Questions from the middle of the room? Just pass it back. No, I'll go first.
Great presentation. I think it's a great set of data. Something that I've been curious about, I know neutron probes tend to be the gold standard of after installation validation. How do you calibrate a neutron probe? I'm curious, or if you do at all.
As far as the calibration of the neutron probe, is that what you're asking? So we took soil samples the day that we installed the tubes at each of those sites. So we installed the tubes, and then we took soil samples and came back from that day at each site, and then brought them back and ran that. So they were specifically at each side.
So it was calibrated for the clay. It's not just simply the
Oh, no,
difference
no.
between
We
the
took-
sand
we-
versus clay.
Put the tube in the ground, took measurements, took cores with it, and then came back and did that, did the calibration.
I thought you had showed a pretty nice graph when you showed the 4 different test beds in the time series. And it looked like, and this is something I've been thinking about now. There's,
Which one?
yeah, that one right there. I like that. That's a really cool graph because it doesn't appear to me that there's like a consistent like one sensor is not consistently overestimating or underestimating. There's no like specific ranking that you could follow in every single test bed, right?
If it's hard to hear, I don't know, I'm sorry, but they were consistent. Yeah, all of them. There was nothing that really, I guess, stood out. There was a couple spikes here or there, like on the right side, you'll see. But for the most part, yeah, they were tracking pretty consistent.
Yeah, and I guess the point, maybe it's more of a point than a question, is that, I don't see any consistent ranking, right? Like in some, on some of those graphs, the CS16 is measuring high, but in some of them it's the Centec, and if there was some specific bias from one sensor to the next, you'd expect them to be consistently ranked, from which one's reading high to which one's reading low, and so I like that you have it tracked against the neutron probe, which is pretty cool. But I also, it makes me think about my own, instruments that I have in the ground stuck in the exact same layer with the exact same sensor, just duplicated, and they can read wildly different. And I think that, if you've ever worked with a Risotron before, think of like a big head-on with a plexiglass front, and unless the thing is totally 100% saturated, if you look at it, it looks like a tie-dye t-shirt. There's the moisture. You think these are consistent beds of homogeneous moisture content, and it's not even close, right? I don't know, it's just food for thought, when we put together these, these sensor test beds, and you're trying to compare sensors, there's the median is incredibly heterogeneous, that you're trying to measure.
Yeah, that's kind of interesting. I wasn't there for either one of these sensor installations. I've seen the pictures. Obviously they talked about what to do when you install sensors and all of that data, the metadata you need to collect. And I've looked through all of that when they did these, and pretty much it looked by the book, just like we were showing earlier. But yeah, there is quite a bit of difference sometimes in those sensors, and they don't have to be very far apart. When you've got vegetation growing on there, anything can happen. But no, nothing really stood out. That's the deal. There were some that were higher and lower on other ones, but for the data for those days or for this year, this is what it was.
Great. Thanks, Jerry. Thanks, everybody. Mike.